Hello, welcome to another episode of Rustacean Station. I'm your host, Alan Wyma, and yeah, it's been a while since we recorded an episode. I'm always looking for new guests and just haven't had a moment to find some. So if you want to come on the podcast, just let me know. Otherwise, today we have a very interesting special guest, I have to say, Fredrik Samson. He's the author of a book from Packt called Asynchronous Programming in Rust. I feel like the async topic has not been touched, and then it seems like everybody's touching the async topic within the past 6 months or something like that. I don't know when you start working on this book, but I'm actually talking to somebody else who's working on another async book. And then there was another book written by, was it Mara Bose, I believe, that came out sometime end of last year or something like that?
Yeah, I think it was Concurrency and Atomics or something like that. Yeah.
Asynchronous is kind of weird because it's simple but yet very complicated. I'm guessing it's because the APIs are simple kind of to use to a certain extent, but the underlying tech behind it is quite complicated, right? Because browsing through the table of contents of your book, as we were talking before the show, you go over a lot of different sections. And I definitely want to crack this open, but we're talking also about listening to podcasts at the gym, right? I had to keep going over it. I'm sure that I'd be reading the same page multiple times, not because I can't pay attention, but because it's just so detailed, I'm sure.
Yeah.
Yeah, I don't even know where to start. I mean, I kind of threw a lot at you. I mean, who are you? I guess we could start with.
Yeah, we can start with who I am. That's a natural place to start. You pronounce my name as good as you can get in English, I believe. So I'm from Norway. I've been programming since I was young, really, but it was first after I finished my studies. And I didn't study computer science. I studied business and administration with strategy and finance. So when I started working, I used programming as kind of a superpower, first in Excel and in different kind of languages at my work, do simple tasks, do data analysis and stuff like that. So that's how it kind of started. When I started at this company, which is an old company that's a family business, I met my first nemesis, which is called the IBM AS400 mainframe. So that's a machine from the early 80s, I believe, that we still had here when I started. And to even get data out of it, you had to be pretty technical. So I started to really leverage my programming skills at that point, and then I started using it a lot at work, and also it developed into a big hobby of mine. That's kind of how I started. I definitely learned programming from the top down by solving tasks that's important for the business, and then more and more technical and more for other areas as well. So I started learning Rust in 2018. At that point, futures wasn't really a part of the language yet. There was a lot of discussions, and there's always been a lot of discussion about async and Rust, but there was a lot of discussion that time on how this design would end up. And after programming in C#, JavaScript, and a host of other languages, I realized when I came to Rust at that point, I didn't know the subject of asynchronous programming as well as I thought. So that's kind of how this journey started for me. And I also started writing the material for this book all the way back in 2018. And it started out as actually me figuring out how to learn asynchronous program from the bottom up. And I realized the information was really hard to get by. You had to read the source code of, C++ libraries, Boost, libuv, Tokyo, Mio. Lots of things had to be really researched to kind of get a good mental model of everything. And I started making that easier for the next me to choose that road and learn asynchronous programming from the bottom up. So I published a set of smaller Git books. And then later I wanted to put everything together because they were kind of disjointed pieces of work. So I wanted to put everything together and rewrite it a second time. And when everything has stabilized in the community, in the async community, things are getting more stable. And I think that's also why you see more material now. Of course, this opportunity presented itself, and I just had to take it. It was going to be now or never to make this book. So that's kind of a little bit of me and the backstory of why I wrote this book in the first place.
Now, did you approach Packt, or they approach you about this?
They approached me. There was a guy there that's read my other books that I had out at the time. They were starting to get a little bit old. They were probably 2-3 years old at the moment. And I just kept them up to date, which was a job in and of itself because a lot of aspects of the language developed so fast. So just keeping the books relevant and correct ended up being quite a bit of work at that point. So I was contacted, and it was just an opportunity. It was at a good time where I had a little bit of surplus time again, and I started having the opportunity to commit to actually putting it all together exactly a year ago, pretty much. So I spent a year to kind of do that and rewrite everything into this book.
The async story for Rust, I mean, has been quite complicated, right? Like you said, because they originally had something like a runtime, I think, a long time ago with some green threads. No, did you look into that?
No, I haven't really looked deeply into that, but they had green threads or fibers or whatever you want to call it. I call them green threads with a runtime. It's similar to what Go has today, something very similar to that before it reached 1.0. But then they removed it, and it was without any async abstraction in the language for many years until you got async await in 2019, I believe. Yeah, something like that. And so it turned out that the green thread model and the runtime, when Rust's value kind of settled on being zero cost and being a systems programming language, it didn't really align with that very well. So that's why it was chosen to take it out and not have anything there for a while until you found a design that was right for Rust. But of course, that evolutionary process creates some confusion for people, right? Because you don't know what to do. There's experimentation in the community and the ecosystem. And some of the difficult parts of Rust today has some historical effects, right? So because, for example, Tokyo is one of the earliest asynchronous runtime we have in Rust. And it started its developing its API before Rust had a concept of async await, for example. So that makes everything a little bit complex.
You said it's 1 year ago, right? So at that time, even I think everything wasn't quite so stable as it is now, or has it been quite stable? It's been a while since I take a look at it.
It's been quite stable the last year, but there's things happening all the time, and I even struggle keeping up to date with the latest development. But the important bits are stable, right? So what's happening is that you want to create async Rust, a more streamlined experience, especially for newcomers and new users of Rust. And there's a lot of work going on there. And there's also some rough edges with async Rust today that's being worked on. But I would say the fundamental parts are pretty stable, right? So they've chosen a way to solve this. They have the async await syntax in the language. They have a concept of futures and wakers, and it seems like the ecosystem has kind of settled on a few ways to use this. Right? You have several popular runtimes, and you even have a popular embedded runtime like Embassy. So it's starting to show itself. But yeah, there's a lot of work still being done, of course. But I would consider it stable, absolutely.
What does it actually mean to be asynchronous, right? Because there's different ways of being asynchronous, and that kind of all depends on the runtime that you have, no?
Yeah, well, we can start. And this is some of the things that make asynchronous programming a little bit difficult because you have to make some definitions on what does asynchronous programming really mean. And I also struggle a little bit getting up with good definition of that in the book. But the primary thing that you do with asynchronous programming is you create an abstraction over concurrent operations. It's often a programming language. It can be a library as well, but you create an abstraction over concurrent operations. So it's how you write a program with a non-sequential concurrent program flow. You often need this when you have a lot of I/O writes, because tasks can interleave. The progress of each task can interleave while you wait for a database query to finish. Another task can do some work, but you can also do this to divide your attention between different tasks, more like a scheduler. And I believe that's pretty much what the Embassy does as an embedded runtime. It kind of serves a little bit the purpose of an operating system scheduler on embedded. So there's other uses for this, but for desktop and server programming, you would most likely encounter this in relation to I/O. So in asynchronous programming, you create an abstraction that we can call a task that's able to be stopped and resumed at specific points. So that means that when you can stop and resume a task, you can have several tasks progress interleave. So you can start task A, stop it, start task B, stop it, and then go back to task A, and so on. And that's kind of at the heart of asynchronous programming. And that's also what makes it a little bit difficult, because we try to make asynchronous programming look like synchronous programming, but what's happening is that something is taking the whole program flow you write and rearranges it. So it's kind of invasive. It's not just a pattern you use. It really takes control over the whole program flow, and that's also why it's called a runtime, right? You need that to actually run your program. That's the basics. So you need an abstraction over these kind of tasks that are going to be stopped and resumed. And in Rust, that's a future, right? A future, the ones you create by async await, they can be stopped and resumed at specific points. And every point it can stop and resume, it will typically yield back to a scheduler that then can schedule a different task. That's the heart of asynchronous programming. It's an abstraction over concurrent operation. And I believe some of what makes asynchronous programming a little bit difficult is the stack of abstractions you get, especially on desktop and server system, because you have the hardware and the real world is mostly asynchronous. We live our lives asynchronously. You would never solve things strictly synchronously like you write a computer program in real life. And the hardware lives in asynchronous world. It doesn't know when you're going to hit the next key on the keyboard or when some data is going to come on a network card, right? And that means also the operating system, which is an abstraction over the hardware, will also have to deal with this fact that things are happening asynchronously. But the operating system presents you with an illusion that everything is synchronously. It gives you a process and a main thread. And to you, as a programmer writing that process or that program, it will seem synchronously. But then in asynchronous programming, we create an abstraction on top of that again that makes everything asynchronous. So now you have two schedulers, right? You have the operating system scheduler that presents you with this sync abstraction we call threads, and you have the runtime scheduler. And now you have to be careful so you don't involve the wrong scheduler at the wrong time. And that's often what you see mentioned when people talk about blocking the event loop and stuff like that. It's actually you involving the OS scheduler when you really want to involve the runtime scheduler, because when you're in an asynchronous system, you never want to involve the operating system scheduler as a user of the system, right? Because that will block also the runtime scheduler and kind of render the whole point on doing it asynchronous in the first place mute, because you invoke the wrong scheduler. So you can't use an operating system like the standard library mutex in an async context, because that mutex, if the thing is trying to take a lock on, it can't take the lock. It will actually park your thread. It will involve the operating system scheduler and tell the operating system this thread can't progress anymore, so you can do other things. Yeah. What happens then is that the whole scheduler, even the runtime scheduler in async, will actually get parked, and you will get nothing done until you can take that lock. So that's why you need a special version of mutex, for example, that works with the runtime instead. And essentially it ends up being an asynchronous copy of the standard library you need, because the standard library will by default involve the OS scheduler numerous places, right? So that makes things a little bit hard to reason about. But it's not, asynchronous programming by concept is not that difficult, right? Because it's tasks you can stop and resume. And it's something that makes sure that the right task is stopped and resumed at the correct point. So at a very high level, it's not that difficult. But the stack of abstraction makes it pretty difficult, actually, to wrap your head around.
I mean, if you think about it, I don't really want my program to be stopped and resumed. I want it to complete, right? What is the point of it kind of having this nicety of a asynchronous program? Because like when you start doing asynchronous work, I mean, I know there's benefits to it, but the problem is like usually for simple apps, you're not really going to see it, right? So the question is for somebody who doesn't really have a very complex app with many users or whatever, much work to do, it's kind of like, why should I care?
That's a very good question. There are several reasons you should care. One of the obvious reasons is that when you write a program today and you use a database driver, or you create a web server, or even if you use a web client, you will probably have to deal with the side that these libraries are async. So it's easier to just go use that version and instead of trying to find blocking alternatives everywhere. But if you write a really simple program, most likely you don't really care and you don't really need asynchronous programming, to be honest with you. But the reason we should care on a little bit larger scale, and once your program is getting a little bit bigger, is efficiency, pretty much. Because that's what asynchronous programming is about. It's about efficiency, making programs more efficient. We can't rely on hardware getting twice as fast every 3 years or so. It's a long time since we could rely on that, right? But since developments on the hardware side are stalling somewhat, they are also working on making their hardware more efficient by having better pipelining, by improving the instruction set, by working on faster memory and things like that, larger caches and more cores on a die. It's not that the speed is getting faster itself at any significant rate anymore. So we as programmers should also write more efficient programs, and then you will need to write them asynchronously, since if you write a program only using the operating system scheduler, you will end up wasting some resources, because the operating system scheduler is a general scheduler. It is created to work on all programs and treat all processes equally. And if you have a web server running, for example, you do something with a lot of I/O, you probably want to take care of the scheduling of those tasks yourself and make sure that each task doesn't take up more memory than it needs and things like that. So that's where it will come in. It will make your program more efficient. And that's also important in this day, right? So power and compute is expensive. So if you can make it more efficient, that reduces cost, and it will be a good thing.
So you're saying the writing your code asynchronously will actually reduce the footprint of the resources required?
Yeah. It depends a little bit on the alternative, but let's say you use operating system threads as an alternative. You take every connection you get. You have a web server, and every connection is handled by spawning an OS thread. That OS thread will occupy a little bit more memory. It will go into the OS scheduler that schedules everything on the system. So it might not prioritize waking your task first. It might go on and progress some other tasks, and also some of this context switching can be somewhat costly when you have a lot of them, especially when you talk about context switches between processes, because as you know, one process is not allowed to access anything that's associated with another process. The system wouldn't be secure that way. So you have to take measures, flush some caches, save some state and stuff like that to switch between this, and that will be add up and can be costly. And honestly, once you start using a very concurrent situation, it gets really complex. It gets, in my eyes, more complex than starting to write your own asynchronous programming from the first place and use a userland scheduler instead, like Tokyo.
Well, I mean, most of us are not really going to be down to the weeds like that, writing our own async runtime, right?
No. And you don't really need to either. But it's nice to know how they work, because once you hit some of the rough edges that's out there, you have slightly complex scenarios, or your program starts to get more complex. It's really nice to know how they work. And it's not that creating a super optimized and a runtime that handles everything is very complex. But how a runtime works at a high level is not really that complex. And it's really helpful to know how they work and get a good mental model of what's really happening when you write asynchronous code, right? So in the book, I divide the runtime into an executor part and a reactor part, which are two different parts of a runtime that's responsible for two different things, and it maps really nicely with the Rust asynchronous model. And I have to say, I also spent some time in the book to actually explain the word executor, because I'm not a native English speaker, and I always called it an executor, not an executor, because I thought it was the executor from the medieval times that were deciding who lived and died, and decided what processes got to live or die in the scheduler. But turns out executors are not called executors at all. They're called executionists. And I don't think they actually decided who lived and died. I think that was settled at that point. But an executor is something that decide who gets time to run on the CPU. And you can think of it as a scheduler, right? And in Rust, you often divide a runtime into a scheduler part and reactor part. That's make sure you get notifications from the operating system when an event has happened, so it can actually wake the executor and schedule your tasks correctly. So creating these kind of mental models makes it easier to understand what happens under the hood and why you need a waker and things like that, because there's a thought behind the design. And once you get that, it makes it easier when you hit a problem to actually figure out the solution and figure out what's going wrong yourself.
Yeah, I definitely hear those terms, right? Do you mind to still go over the pieces? So you're saying there's basically only two pieces when it comes to any kind of runtime?
Well, I think it's a good mental model to use, and I don't know if everyone uses those terms today. I think someone calls it a driver and a scheduler and stuff like that. I see in all kinds of naming on them, but usually a runtime is divided into those two main parts. And you have a reactor that kind of presents you with something that represent, for example, I/O, right? It can give you a TCP stream, for example. And it makes sure that this TCP stream is different from the one you have in the standard library, in the way that it won't actually yield to the operating system scheduler. What it does is that it simply will register that task with the reactor, which will communicate. The reactor will communicate with the operating system, and by EPOL IOU ring, I guess you could use, it's probably going to be used at some point, KQ or IOCP. And it will make sure that it gets notified when something is ready on that TCP stream. So when you use that, you're communicating with the reactor that makes sure to handle everything with the operating system. And when the operating system comes back and says, okay, I have an event ready for this, some data is ready on this TCP stream, the reactor will wake up the executor, and it will arrange so that your task is put in the run queue as ready, because now your task can progress. And the executor will then look at what tasks are ready, and it will decide, okay, now you can run, now you can run, now you can run, and make sure you progress to the next step next time you hit something that you will block on. And by modeling runtimes like that, it makes it easier to understand. It also makes it easier to understand why we have a waker in Rust. But it's the way that the reactor and the executor communicates. So the reactor will call wake, which is something that wakes up the executor. So they don't really need that direct dependency. But in Rust, usually they come in the same package. So you will always see them packaged together in a runtime. But understanding how that works can also open your eyes a little bit and makes it easier to understand why, if you try to use a TCP stream from the Tokyo library, but you want to use it on a different executor, you want to use it on a scheduler from async stud or small, you will get an error saying that you don't have a runtime, Tokyo runtime using. But that's because that TCP stream wants to register with a reactor, and that reactor is part of Tokyo. So you have to start at least the reactor part of Tokyo. You don't need to use the scheduler. You have to register that so something can call wake when that TCP stream is ready. And it will then wake not the Tokyo scheduler, it will wake the small or async stud scheduler. But these kind of things are difficult to understand if you don't have some kind of way to model this. You end up using asynchronous Rust the way you would use it in C#. You end up with these corner cases like that. And you think, wow, this is just really complex and confusing. So by explaining it and giving everything names and explaining how it works, I'm hoping that it will make it a lot easier to kind of understand what's going on. Because once you know that, it's an easy problem to fix, but it's not intuitive, right?
Okay, interesting. I didn't even think about mixing and matching because, like you said, I always think about them coming as some kind of cohesive pair that can never be split up. Right. And now that you mentioned this, okay, it does make sense that they would be very closely linked. Would you ever really want to like pair things from one runtime to another? I mean, to me, I don't think you'd want to do that because like I think they usually have similar names or something. I'm just saying like in general, like would you actually want to do that? Of course you cannot, it sounds like. Why would you even want to even think about that? It's the thing that comes to my mind.
A couple of things. First of all, if you start a new project today, that's not the way you would start, right? You would pick one runtime and the ecosystem surrounding it and try to stick with that. But sometimes you hit these cases where something is made using, or it could be the other way around, you know? Tokyo is very popular, and you will often see that some library, a database driver, is written with Tokyo in mind. And sometimes it depends a little bit on the library. You can use that on a different runtime if you chose that as your runtime for your main program, or you need something to kind of hook two different pieces together. But the clear recommendation, of course, is to make it easy on yourself, is to stick with one runtime, because then you don't have to care about these differences. But at some point you end up with these kind of errors. I think pretty much everyone that has done asynchronous programming in Rust to some extent has ended up with errors like that. So you need to know how to handle them, I believe, at least at the current state of asynchronous Rust.
Yeah, I believe there's a working group working on trying to make it so that you can actually easily swap out your runtime, because really that should be more of a program design rather than, say, a library specific design. You know, I mean, that would make more sense to me, right?
Yeah, I know there's work going on there. It just turns out to be really difficult to create one API and agree on an API that's zero cost in all kind of scenarios, and something people would want to use and agree upon. So that's kind of the difficult part, because of course it would be easier if you can kind of swap runtime, but that means you have to agree on the same APIs. And there's some APIs that are difficult. You know, if you use a web server, that web server will definitely need to spawn tasks on the executor. But the way you spawn tasks on an executor is not equal across all runtimes in Rust, right? So then to kind of force everything to be equal, Rust needs to have a spawn trait, for example. So you can use that trait to spawn a task on the scheduler, then you would have one problem solved, right? But getting that to be zero cost in all circumstances is a difficult task, and it will take time. But I believe we will get there sometimes, where there's either patterns or abstractions that will kind of make this easier than it is today. But it will take some time still.
Luckily, we have, I think, at least 90% of projects out there basically handle, or work with Tokyo. So that's nice that we can say, okay, just go for Tokyo. But for the people that cannot use Tokyo for whatever reason, I think embedded systems is a big problem with Tokyo. I think Small, I believe, can work on that. It's been a while since I've looked at these. Maybe not. Is it Minio or something? There's one that for sure can work on embedded systems. That would make much more sense if you could just swap them out. But it's really one of those problems that, like you said, I'm aware it's very difficult to solve. But at least to hear that you're optimistic about that being solved is good to hear. Because to me, I don't know how much progress we've made recently, but I know it's very difficult to do. Like you said, every runtime system has its own needs and wants, right? And it's hard to rope everybody together.
Yeah, and that takes a lot of time. And the way Rust kind of does this also is to kind of leave it a little bit up to the community and ecosystem to figure out the best way going forward. And of course, that results in a lot of discussion and, even discussions that are emotional, right? Because you get invested in ideas and it will end up with a really good end result, I'm 100% sure. But the road there is a little bit rocky. Whether everything in Rust is going to be plug and playable, I don't believe that's going to happen. But I'm pretty sure there's going to be paths you can take that make everything very straightforward and easy. But that will take years, I believe, to get there. But it's not that bad today either. But you need a little bit more knowledge to kind of not end up being frustrated of the state of things today.
I know there is a couple of libraries that manage to somehow make things somewhat easy for different ones. I think ZBus is one that they're able to support different runtimes, if I remember correctly. It's been a while since I've looked at this.
Yeah.
But there's definitely a couple out there that manage to be kind of runtime specific free.
Yeah, it's an interesting thing because if you look at Isaac, for example, it's an executor agnostic HTTP client. But it solves it by kind of bringing its own reactor part. We talked about reactors earlier. So it kind of brings it on and starts that on its own. It uses libcurl under the hood. So libcurl will actually the callback you pass in there will kind of act as a reactor in this case. But when you do it like that, you can have a library that's used across runtimes. There's other ways to solve this as well. Some libraries, I think Hyper has a spawn trait that you can use. So if you implement that for something else than Tokyo, you can in theory use that runtime. But right now, the libraries solve this in different ways, and there's not like one good way of solving it. So I'm kind of hoping there will be patterns or abstractions that makes that easier for the circumstances where it makes sense. But right now it seems like a lot is kind of evolving around the Tokyo runtime, and if you stay within that ecosystem, you will have a fairly easy time, right? Because things will mostly work out of the box as long as you're in that ecosystem.
I kind of wanted to get into a couple of things. Like we talked a little bit about threads, right? And then you did mention fibers and green threads. Can you talk a little bit about the differences between the two and why you might prefer one of the other? I mean, are green threads and fibers the same thing?
Well, that's one of the funny things. I think you will see people call different things green threads. I know there is somewhere in the Tokyo docs that says it's a green threads for Rust. I don't believe that there's a clear definition of what green threads are. But the way I use it, and I see a lot of people use it, is more related to a specific implementation of what we call stackful coroutines, which is what Go uses, for example, and what Rust had before 1.0. And it's a totally different way of creating an abstraction over concurrent operations than you do with async await in Rust. I kind of view them as two very popular ways, very different, but kind of aims to solve the same problem of making asynchronous programming easy to use and hard to misuse. To talk a little bit about the differences, there's a lot of them, but if you look a little bit about what makes them different, what I think is really cool with green threads, and why I included an example of that in the book, is that green threads are very similar to operating system threads, right? You set up a stack that's suitable for the operating system and the architecture you're on, and you make your CPU jump to that stack and just use that as a regular stack, as a stack you would get provided by the operating system. That's really, I think, technically and conceptually really cool and really interesting. But what happens is that you create tons of threads. Like these threads, you can decide 100% yourself how big the stack is going to be, how you will grow the stack, how you handle stack overflows. You probably wouldn't have stack overflows on a stack like that, but you might run out of stack space and you need to handle that somehow. So you need to handle the fact that if you allocate that too small stack, you will have to grow that stack, or you have to create a new stack and accept the fact that your stacks are now disjointed pieces of memory, which is complicated. And we even have an implementation of that in Rust people can check out. It's called May, that implements stackful coroutines for Rust, or green threads as I call them, and a lot of people call them. So the thing about those is that you can mostly use them and program against them like you would with operating system threads, because they're very similar. The difference is that these are handled and scheduled in user land, as we call it, by your program. The operating system doesn't know about them. And that makes them pretty easy to reason about and to use. You don't need pinning. You don't need any concepts like that. You have your own stack. It will mostly work like it would if you use operating system threads. There are some drawbacks, however. The one thing is that to make them more efficient than operating system threads, you kind of have to allocate less stack space for each task. If you just allocate a huge amount of stack space, you will theoretically waste space. And secondly, they're pretty difficult to use with FFI, because when you use FFI, or the foreign function interface, the operating system will assume that these functions are called from a regular stack and not one of your fibers or green threads. So that means that when you use FFI, you will have to go back to the main thread you were using, basically. And that will make it really difficult. So Go has issues with this that makes FFI difficult to use. And that's one of the reasons I believe it's not really suitable for Rust either. But you also have the opportunity to preempt these tasks, because when you have a stack like that, you can stop and resume execution at any point in time. You don't have to care whether you're in the middle of a function call. You can just theoretically stop the execution at any point in time. So that makes preemption, like having the scheduler force this task to stop, easier to implement. And I believe Go has had that since version 1.14, which is nice, because then you can have a failsafe if some tasks are occupying all the CPU time. You can actually make sure there's some fairness into the system, that you can actually stop that task and give others time to progress as well. So Rust solves this a very different way, where you don't create these stacks that's similar to what the operating system does. Rust creates it by rewriting your programs. So when you write an async function in Rust, it can fool you because it looks like a regular function, but it's not at all. What happens is that this is getting rewritten into a state machine, and I believe many people have probably heard about that, but it turns into something very different from what it looks like when you write it in your editor. By doing it so, you're kind of just writing a normal program. So all you do is kind of rewriting pieces of code to make the tasks stoppable and resumable at different states, which makes them very memory efficient, for example, because you don't have to pre-allocate any stack space and things like that. And you don't have to worry about context switches where the CPU has to jump from one stack to the next and things like that. But you need things like pinning, for example, and then you need other stuff. It's not like there's one solution that's better in all cases than the other, but in my eyes, it makes a lot of sense the way Rust has solved this the way it has.
That's a lot of information to pull in. A lot of languages that I work with, at least specifically like Elixir and Erlang, they do have some kind of green thread-like system. And it works out quite well. They really have like these things called schedulers. They got one per core, so that way you can run stuff multi-core. And they have a couple of, like IO threads that whenever you're doing something with IO, they'll just show it to that kind of scheduler like thing. They don't actually call that one a scheduler, I think. But in any case, like it's pretty interesting to start to understand this stuff and to see it. And I think Tokyo also does some kind of green thread based system, no?
Well, they call it green threads, and I would call them, that's what's kind of confusing, because the way at least I view green threads and see it mostly used, it's the stackful coroutine kind. So Tokyo doesn't do stackful coroutines, they do stackless coroutines, which is the kind we get from async await in Rust. But you will see people call that green threads, because if you think about it, what a thread is, it's just a thread of execution. So when you say an OS thread, it's just a thread of execution. It's an abstraction the OS uses. So when you see a green thread, it just means a user land thread. A thread that's not in the operating system is created in user land, right? So that can mean any thread of execution, really. So it's really general in that sense. But I mostly use it to mean stackful coroutines or fibers, the kind you have in Go. I see people use it for everything that's a user land abstraction for a thread of execution.
Coming off of, green threads, fibers, and threads, right? I was just looking at your book, and in the next section you have about ePull, KQ, IOCP. Wow, I mean, as somebody who does mostly high-level languages, I feel like I'm just reading Latin or something totally outside of my scope. I do know that people say, oh, you should use, I think there's something called a U-ring. Why should I really care about this kind of stuff? Or does it actually make sense for me to actually dig in deep to these things if I'm just writing a normal program? Or is this something that people need to learn once they hit a wall of something?
To answer your question, do you need to dig deep into it? No, I don't believe you do that. But is it useful to know about it and how it works? I think it is, absolutely. Also for the fact that one thing is actually getting by doing asynchronous programming, but sometimes you end up in discussions. What is the best choice to make here? Why are we choosing IOU ring? I don't even know how to pronounce that because I only read it, but I guess that's how you pronounce it, instead of ePull. You will end up in discussions around design choices that makes it really useful to know what they are. And again, it's a concept that's pretty easy on the high level. The difficulty comes when you look at the concrete implementations, because have a lot of historical baggage and also are not created to be intuitive. They're created to be useful at a very low level. But you can kind of divide these things into completion-based or readiness APIs. That simply means that the operating system maintains some kind of queue of sources or things that you are interested in getting notified in events on. And IOU ring and IOCP are completion based. So the operating system will get back to you once a task has completed. For example, if you say, I'm interested in knowing when there's data ready on this TCP stream or this socket. The completion-based interfaces like IOU ring and IOCP, with those you will actually hand over a buffer and say, please read this data into this when it arrives and let me know when it's done. With the readiness-based APIs like ePull and KQ, you're saying, let me know when I can read data from this socket, so you don't pass on the buffer. So that's a big difference, right? Because the operating system can make things more efficient the more it can handle, because it's the closest part to the hardware. It comes with also some downsides, but today you mostly see abstractions that cover IOCP, which is completion based on a Windows API, and KQ and ePull, or that's readiness based. For KQ is for Mac OS and BSD systems, and ePull is for Linux. So by knowing these differences and also taking a little bit look at what ePull is, especially since Rust kind of models so much of its system after a poll-based model, it really will put some pieces of the puzzles in place. But do you need to know everything about it? No, you don't. And honestly, some of the APIs are pretty difficult to work with. But in the book, for example, we get something working with ePull just to see how it uses and what's the difference between a level triggered and an edge triggered event, for example. And it's a really interesting thing because it kind of maps a little bit back to how hardware services interrupts, right? So all of this kind of, you will get the pieces of the puzzle that kind of fits together, and I believe it's really useful to know about it. You don't need everything to kind of get by.
That makes more sense. Yeah, I think I talked with a couple of people before in the past, and it's hard to keep track of this stuff if you're not working with them every day or involved in that kind of stuff. It's interesting in here. You also get to create your own event queue and create your own fibers, so you can kind of start to understand how those things basically work at a somewhat lower level, right?
Yeah, it's a little bit tangential, I would say, to understanding futures in Rust. So, of course, the book goes in detail where you create your own alternative version of futures in Rust. You kind of go like Rust's history in 5 minutes, these kind of shows where you go through 100 years of history in 5 minutes. You kind of recreate some of the important parts of that history by creating your own abstractions over it. And that's really interesting in understanding how async Rust works. But these other parts, I think are just really cool and interesting examples, and it will really make you more confident when you deal with asynchronous stuff, to knowing about them. And it doesn't take that much time to kind of at least get a high level understanding of how they work and create your own example. And you can take the example and you can expand on it, you can pick it apart, you can do whatever you want with it, or you can just run it and see that it does what it does. It's kind of up to you, so how deep you want to go in it, but kind of see it and do it. I think it's really valuable personally, and that's how I like to learn myself.
I find it quite interesting that you really go from the bottom all the way up to the top, which is actually kind of nice to see because you can start to understand basically what is the phrase again? It's like how the chocolate's made or something.
How the sausage is made, I believe. You get a little bit of that. And once you get a little bit deeper, there's a lot of edge cases and, as I said, history and baggage throughout the years. But I find it really interesting. And I think and hope other people as well will find it equally interesting.
I definitely will find this one interesting. I mean, I would love to just sit here for probably should do that next weekend. This coming weekends, just sit there and just go through this book because it's going to answer a lot of questions I have about all this stuff.
I really enjoy it. I have to say, as time has kind of been less of a luxury, I have time to dig deep into stuff, at least for parts of the lives with kids and stuff like that. But having the opportunity to kind of sit down and figure out how something works and really go down every rabbit hole, some of them you wish you didn't peek down to, some of them you're super glad you went down to. I think that's very, very fun and interesting myself. And that's why this book was created. It's just because I found that so interesting, but I wanted to make it easier because it took too many hours to kind of figure some of these things out. So you'll cut a couple of 1,000 hours, or at least 1,000 hours, by getting it served a little bit easier.
Yeah, this book, like I said, is definitely super interesting. So you said you started writing about 1 year ago. For all the material that it looks like it covers, it seems like it should be longer than only a year. But I'm guessing, like you said, 2018, you kind of started. So basically, there was some seeds of this book in there, no?
Most of the research, which is the time-consuming parts, right? Especially in places where you can't use a high-quality source, you have to read the source code and you have to kind of double and triple check that the way you understand it is correct enough that you can actually write it as a fact to someone. That part took a lot of time, but I did most of that back in 2018, 19, and 2020, and also the early days of COVID. By chance, I had the doubly slipped disc back in 2018, and I got 18 weeks where I was tied to the bed, and there was very little to do. So I kind of saw that as an opportunity you rarely get when you're an adult, to be able to spend 3 months just reading, learning new stuff. So the research, I think I kind of counted 1,700 hours, I guess, for this book. A lot of that was done over many years, and it resulted in me writing these kind of Git books. So I already knew what I was going to do. So when I wrote this book, I had to write it the second time because you do it better the second time you do something. And I created a couple of new examples and stuff like that. But a lot of the research I already kind of had done. If I hadn't done that, there was no way I was going to finish this in 1 year.
Yeah, I can see that from all the stuff that you cover. I like to kind of simplify prerequisites for this book, right? Because you do go into a lot of deep stuff. If somebody's brand new to Rust, is working in higher level languages before this, should they pick this up? Or is it something for maybe more seasoned Rust programmers?
The thing is that a lot of the book is actually a little bit language agnostic, I would say. We use Rust for the examples and stuff like that. It's knowledge that you can take away and will help you in other languages as well. I would say you should probably have read the Rust programming language, the introductory book. But I make very sure, since I'm not from the background of having programmed in C and I've made operating systems before myself, I make very sure to not assume a lot of knowledge on behalf of the reader. So I try to make sure that if I introduce concepts in Rust that are not covered in the Rust programming language book, I do introduce them really thoroughly. So when we go through inline assembly, for example, in Rust, I make sure you know everything you need to know about the syntax, and the same with FFI and these things. So a lot of the book does take time. So if you're an advanced user of Rust, I would say you can probably skip some of those explanations because you would probably know them already. But I made it so that you don't need that much programming experience, but you should probably have read the Rust programming language, the introductory book that's out there, so you know the basic syntax, what a crate is and stuff like that, because I won't cover that. I will assume you have Rust installed and stuff like that.
That's good to hear, right? So, because I'm kind of curious about, who's the target audience, right? And I think you made that quite clear. So that I won't be too put off to get into this book then. I think I can definitely do it.
I think so. You can definitely do it. And the chapter on green threads is very technical, but you can kind of go through it and see how it does. And if it interests you, you can kind of dig really deep into it. But you will definitely get by. I'm not worried the second.
Good. Is there a specific chapter that is like your most favorite chapter that you worked on or that you think has the most information for everybody?
The thing I was most happy about in this book, and I like the introductory chapters and stuff like that because there are some mental models I think are pretty good. At least it clicks for me when I read it. But when you come to chapter 6 and onwards, where we talk about futures in Rust, I found a way to kind of create this evolutionary version of your code base that ends up being a fully functioning asynchronous Rust runtime. And I think the way we do that and the way we use that to discover things like Waker and things like pinning, that's super easy. Pinning Rust is super easy to understand what it does, but it's super difficult to get your head around how it's implemented in the language and the type system and exactly what it does. It's kind of hard to understand and wrap your head around. But once you see it, why we need it and how it's used, and I'm very happy about how those parts turned out, to be honest, because I felt it's a new way of explaining things that I haven't seen anywhere before. And that's also a little cool. So I'm a little bit proud about that. It's just difficult for me, you know. I'm kind of hoping that others feel the same kind of enthusiasm about that as I do. But I guess I have to wait to see until people have enough time to read it, because it's only been out for it's 2 weeks tomorrow.
One more thing too that I think is really important to talk about is that you're not really taking a penny from this, if I remember correctly, right?
I decided when I made the book, first of all, I didn't make the book because of the money, because it wouldn't justify the time spent on it anyway. So I decided I wanted to give something back to the communities. And I found that the best way to do that was for me to give away 50% of what I make from the book in the following months. So I decided to give away 50% of what I make on the book goes directly to Jon Jengset, which is a Norwegian as well, that I had the pleasure to meet. A very nice guy. And he makes a lot of educational material for us. There are lots of videos on YouTube. He was probably one of the ones that took initiative to this kind of podcast station as well, I believe. So he's been there a long time. I know he's really committed to Rust and wants to create more free educational intermediate material for Rust users. So I decided to sponsor him with 50%. The other 50% is going to my kids. So it's true, I'm getting nothing, but indirectly, since I had to take time away from them writing this book in the evenings, that's how I kind of got an okay in my home. So yeah, I view this as I mostly do this because I think it's really interesting, fun, and I think there should be a book like this. I wish there was a book like this when I learned it, to be honest. So it's a kind of a feel-good thing to do as well, because the people that buys this book will also contribute to educational material for us, that for people that don't buy the book, and it will be other stuff that Jon probably covers in his material. But for me, it felt like the right thing to do, and I wanted to do that. So yeah.
Awesome. Is there anything that we didn't touch upon that you wanted to touch upon?
I thought I kind of mentioned some podcasts that I think is really cool for the Rust community. And obviously this is one of them, but there's some other ones I thought I'd mention because I know you and I both like podcasts. And then there's a couple of ones I think is really cool that's centered around Rust. The other one is a new one called Rust in Production that I think is really cool, where they cover real life use cases of Rust. That's really interesting. And there's a series I really love called On the Metal, made by the Oxide Computer Company. And I think I heard every episode there 7 times. It is not an ongoing series, but it's an old one now, but it's really good. And it also covers Rust some of the time, you know, because Oxide Computer Company is kind of based around using Rust in their tech stack. And you have chats with James that I really love. So I kind of wanted to give a small shout out to that because I so enjoy the content that's being created for us to enjoy. So, and thank you also for making this podcast. That goes without saying.
I thank you for that, and I'm really happy that you wrote this book, and I get a copy of it so I can go through it, because this is something I've been looking to get into, because it's like the one thing that I've just been avoiding. I'm a little bit worried and scared to get into async Rust, but yeah, I know that at some point I have to get into async Rust, so I think this is a good step for me, because I do have some complicated programs I am starting to work on, and I think that I should probably start to use async Rust for the better of the world.
Yeah, I think it's nothing to be afraid of, and people learn differently, you know. But if you're like me, I think something like this will make it a lot less scary to kind of just use. And if you hit any problems, I hope you feel pretty confident in figuring it out, because you will know more than most people, at least to what you know today, I believe.
I think so, based on our discussions and listening to what you have to say. I mean, I think I just had to go through and just read it myself. One thing to listen, another thing to actually read about it and try it yourself. So I'm looking forward to going through this. Again, thanks for coming on. I appreciate your time, and I'm looking forward to part 2 maybe in a couple of years.
Thank you very much for having me on.